Okay, welcome everyone to the 66th meeting of New Directions in Group Theory and Triangulated Categories. Today our speaker is Marion Boucrot from Grenoble, and the title of her talk is The Relation Between A-Infinity Morphisms and Pre-Calabi-Yau Morphisms.
So hello everyone, and thank you for the invitation. So I will begin with sharing my screen for the slides. Yeah, it's okay. And then go for the presentation. So can you all see this thing? It's okay. So today I will talk about the relation between A-infinity morphisms and pre-Calabi-Yau morphisms. So I will talk about 4 different notions. So the notion of A-infinity algebras, which were introduced by James Tashev in the 60s. I will also talk about the notion of cyclic A-infinity algebras, which were introduced by Maxim Kontsevich. I will also talk about the notion of double Poisson algebras, which is a notion introduced by Michel Vandenberg in 2007. And I will talk about the most important notion for me, which is the notion of pre-Calabi-Yau algebras, which was introduced by Maxim Kontsevich and Vlassopoulos. So in fact, there is a link between those notions. So for example, the notion of a double structure on some graded vector space A is kind of an example of a pre-Calabi-Yau structure on this same vector space A, and also given a double Poisson structure on a graded vector space A, one can produce a cyclic infinite structure on the boundary construction A plus A star. And we have so a pre-Calabi-Yau structure on any graded vector space A will also induce a cyclic infinite structure on A plus A star. And moreover, if the graded vector space considered is finite dimensional, then a cyclic infinite structure on A plus A star will induce a pre-Calabi-Yau structure. So for a finite dimensional graded vector space, this is kind of an equivalence. So the motivation for looking at the relation between A-infinity morphisms and pre-Calabi-Yau morphisms are the following. So a theorem by Yeung say that a double Poisson structure on a graded vector space is an example of pre-Calabi-Yau structure. And we have this theorem by David Fernandez and Herscovich saying that if we have 2 finite dimensional double Poisson algebras A and B and a morphism between them, then one can produce cyclic infinite structure on those 2 boundary constructions. So this comes from the relation between double Poisson algebra and cyclic infinity algebras. And depending on the morphism between the double Poisson algebras, we are also able to produce an almost cyclic infinite structure on the graded vector space A plus B star with some shift, and also to produce strict infinity morphisms like this. So the aim of this talk is to generalize in some sense this theorem by replacing double Poisson algebras by pre-Calabi-Yau algebras, and it will lead to a similar construction. So the plan is the following one. I will first present the notion of A-infinity algebras and pre-Calabi-Yau algebras, and also recall the relation that we have between them. And then I will talk about the notion of A-infinity morphisms and pre-Calabi-Yau morphism, and state and sketch the proof of the main result for the relation between A-infinity morphisms and pre-Calabi-Yau morphisms. So I will start with some notation. So we will work over a field K of characteristic 0. A and B will denote graded vector spaces. I will use this set as a set of indices for the pre-Calabi-Yau case. So the first component is n star being the set of natural integers beginning at 1. So this doesn't include 0. And the other component, so for example, the component tk, is n at the power k, where n is now the set of natural integers beginning at 0. I will also denote by this fancy the graded vector space, which is formed by sums of linear homogeneous maps from A to B. And I will denote by A star the graded dual, the graded linear dual of A. Also, I record that we have maps. So given graded vector spaces V1 to Vn, one can define a map on the elements. So we have the data of a permutation sigma. And so this map will be the permutation of the elements. Here, the plus or minus denotes the natural, so the usual causal sign. And I will not give you all the signs for this talk, but all the signs come from the usual causal rule and are uniquely determined by the elements here. So I will now begin by recall what an infinity algebra is, and I will begin by giving the definition of the space of Hochschild cochains. So if A is a graded vector space, the space of Hochschild cochains on A is the graded vector space denoted by C of A, which is a product of graded vector spaces that are given like this. So we have, so this is the graded Ohm, and we have maps going from a tensor product of copies of A1 to A. So as a remark, an element on the shifted Hochschild cochain will induce map like this, just using the isomorphism we have between the Ohm shifted by 1 and the same Ohm with the output shifted by 1. So we have no sign here for this isomorphism, and we will represent a homogeneous elements in this shifted Hochschild cochains like this. So if we have, for example, a map F going from this space to this one, here the double arrow is just a representation for n consecutive incoming arrows that represent all the inputs here of the map. And the outgoing arrow here represent the output. Note that this outgoing arrow is bold, and the bold arrow in a diagram will mean that this arrow is shifted. So I will now give you the definition of an infinite structure on a graded vector space. So this is an element of the shifted Hochschild cochains, which is of degree 1, and which satisfies the Stashev identity. So we ask that for all n in n star, we have this identity. So one can depict this left member as this in order to understand better the identity. So we have here an element SMA of the shifted Hochschild cochains that will take some identity maps here. The output of another map on the space of Hochschild cochains, and then other identity maps. So we ask this to have an infinite structure, and obviously an infinity algebra is just the data of a graded vector space together with an infinite structure. So I will now record the notion of cyclic infinity algebras. So if I fix a homogeneous bilinear form gamma, an almost cyclic infinite structure with respect to this bilinear form is an infinite structure that satisfies this identity. So here we apply gamma to S of MA, so this is the infinite structure, which takes as an argument lots of elements of A, and here we have another element which is an element of A, so in fact of A shifted by 1, and we want this to be equal at almost the same thing up to a sign, where we have permute this last element with all the other to put it at the beginning. So we want to have all this identity to have a normal cyclic infinite structure. And if the bilinear form that is fixed is non-degenerate, we will say instead of almost cyclic that we have a cyclic infinite structure.
Excuse me, do you want this form to be skew symmetric or symmetric? Or nothing?
That's a good question. I think that it's, let me think. I think that we can give this definition for all the homogeneous bilinear form, if I'm not mistaken. But I will work with particular bilinear form that will be skew symmetric.
Yeah, and also form gamma could be maybe take value on shifted k, not k itself. It could
Here?
be, yeah, it could be shifted by any integer, I suppose.
Yeah, it could be. Yeah, in fact, the bilinear form can have any degree, and I think that if the degree is not 0, then it's like we have a shift here.
Yeah.
So it's possible, yes, to have a shift of k instead of k itself. So I will work with particular bilinear form that will be skew symmetric by their construction. So namely, if I take a homogeneous linear map from A to B, so A and B are graded vector spaces, and I consider a map, I will define the phi mixed bilinear form as this bilinear form gamma phi, which is of degree d plus 2, and which is given like this. So if I have an element of B star and an element of A, gamma of phi is just up to a sign this evaluation. So we compose the element f of B star with the map phi going from A to B, and we apply it on A. And here we add the correct sign to have a skew symmetric bilinear form, meaning that here, so this has to be the same as this in order to have a skew symmetric bilinear form. And also we define this bilinear form gamma phi to be 0 if we applied it on either 2 elements of B star or 2 elements of A. An example of some kind of phi mixed bilinear form is the identity mixed bilinear form. So it's just called a natural bilinear form. And it is when B equals A, the bilinear form, the phi mixed bilinear form where phi is the identity from A to A. So this particular natural bilinear form will be denoted gamma of A. Also, this natural bilinear form is non-degenerate, provided that A is a finite dimensional graded vector space, but the phi mixed bilinear form is not in general, even if both A and B are finite dimensional. So we will work at some point with almost cyclic infinite structure, meaning that there are some kind of cyclic, but with some bilinear form that is not non-degenerate. So we'll work more particularly with those 2 bilinear forms. And now I will begin with the definition of pre-Calabi-Yau algebras. And first I will define, as for the infinity case, a new graded vector space that is called, following an article by Yeung, the multidual space. So if we have vector space, graded vector spaces A and B, the multidual of A and B is this graded vector spaces given as a product of graded vector spaces, which are the graded vector space of, so this is the graded OM of maps that are now going from lots of groups of input in some sense. So we have tensor product of copies of A1 of A shifted by 1 many times, and we have now several outputs in B shifted by minus D. So we'll denote just by multi of A, the multidual of A and itself when both A and B are the same. And as for the case of an element of the space of Orchil cochains, it is possible to represent by a disk an element of this multidual. So Now the disk must have several outputs here. So we have several outgoing arrows, and we have double arrows that again represent consecutive incoming arrows. So a disk is of type N1 to Nk. If we have here N1 consecutive incoming arrows, then we have an output separating the second group of inputs, and here we have N2 incoming arrows, etc. So also this disk represents this element, so we'll denote it like this. So we'll say in some sense that F N1 to Nk is this disk. Yeah, we will really make this correspondence between the maps and the disks. So we have an action of this multi-dual space, which is given, so this is an action of the product of the Cn, where Cn is the subgroup of Sn formed only by cyclic permutations. And so given an element in Cn, so in the product of all the Cn and an element of F, this action is the element which is given by here, make the permutation of the groups of inputs, then apply the corresponding component of the map F, and then make the inverse permutation for the outputs. So the invariant multidual of A and B is just the graded vector space denoted like this with the T here, which is formed by elements of the multidual of A and B that are invariant under the action that I just defined here. So as before, I can shift an element of the invariant multidual now by D+1. And an element shifted like this will induce two types of maps. So here, this is the choice of apply the shift to an output of the map, which is like we do, like we did just before for the space of Orchil cochains. And here, this is the choice of applying the shift, so a shift now of -d-1 to an input of the map. So before giving you the definition of pre-Calabi-Yau algebras, I will just explain how to compose some disks like this. And I will talk about the notion of diagram. So a diagram is, roughly speaking, a finite connected collection of disks with incoming and outgoing arrows without any cycle and with a clockwise labeling of the outgoing arrows. So for example, here we have a collection of 3 disks. This collection is connected because each of the disks shares an arrow with another one. We don't have any cycle because I can go from an output and turn around the diagram, passing through all the inputs, the incoming and outgoing arrows. And also I have a clockwise labeling of the outgoing arrows. So now the type of a diagram is just the topo of integers. So for example, here we will have 6 integers, n1 to n6. N1 is the number of incoming arrows between the outgoing arrows 6 and 1. N2 will be the number of incoming arrows between 1 and 2. Here we will have to add this number of incoming arrow to this one in order to have all the incoming arrows between the outgoing arrow 2 and the outgoing arrow 3. And so this defines what is the type of a diagram. So it's also possible to associate a diagram to a diagram and some elements of the multidual map, namely given a diagram G, which is composed of n disks and which is of this type. And if I have also n elements of the multidual, so the same number as the number of disks, I can define an element in this component of the multidual, where here we have the type of the diagram. So the association is as follows. So if we have the same diagram as before and elements of the multidual of A and B, we will define this element as the composition of, so the shift by D plus 1 of those three elements, and we will follow, for doing the composition, the shape of the diagram. So I have to apply here the shift because the multidual, so in the input we have copies of A shifted by 1, and in the output we have copies of B shifted by minus D. So here, sorry, I have to take just the multidual of A. So all the inputs and outputs are in A. So here we don't have the B, and here we also don't have the B. And so I will first put all the elements in the incoming arrows of the diagram. Then I will apply here the source of the diagram, which is the disk which shares none of its incoming arrows with another one. Applying G to elements will give us a tensor product with 3 tensor factors. I will use 2 of those tensor factors, one for applying F and one in order to apply H. And then I will apply F on all the elements in the incoming arrows, and I will do the same for H. So here I don't have any more labeling by integers of the outgoing arrows, because I will, by convention, take the bold output of the diagram to be the last one. So this is the first elements we will have in the result. This is the second, this is the third, etc. Also, here I have shift an output of F, and here I can't have shift to output of G, because in some sense, G only has one shift. So this means that this is a shifted output of G, and this has to be seen as a shifted input of F. So I'm now ready to give you the notion, so the definition of pre-Calabi-Yau algebras. So a pre-Calabi-Yau structure on a graded vector space A will be an element of the shifted invariant multidual of A, which will be of degree 1 and which will satisfy the those identity. So those identity are related with those diagram. So this will be the diagram D, and this will be D prime. So here we have 2 ways of composing the pre-Calabi-Yau structures. So here we have shifted an output of MA and an output of this one, and we have so make this composition as defined by the composition of disks. And here we have shifted the output of this one and shifted an input of this one in order to compose the 2. So this is the first difference, and the second difference is that here we have so the last outgoing arrow of the diagram, which is on this MA, which receive in some sense an input from this MA, and here the last outgoing arrow is on this MA, which will give one of its output to the other. So if we sum over all the diagram of a given type, which are of this form, namely with 2 MA and with a bold outgoing arrow on this MA, and also if we sum with all the diagram of a given type, so the same type as before, N1 to NK, let's say. So we sum all the diagram of this type with now the bold arrow on this MA, we ask this sum to be 0, and we have so like a generalization of the Stashev identities, which give, if they are satisfied, a pre-Calabi-Yau structure on A. So in fact, the original definition used the necklace bracket. So this definition is tantamount to require that the necklace bracket of this element with itself is 0. And this necklace bracket is in fact a graded Lie bracket on this shifted invariant multidual. And it's in some sense related with the Gerstenhaber bracket. The Gerstenhaber bracket is the one used for defining infinity algebras. So, okay, do you have any question at this point of the talk? Or okay. So now I will explain how cyclic infinity algebras and pre-Calabi-Yau algebras are related. I will first define an injective map going from the shifted multidual to this space. So this space is the home of, so here we have lots of copies of A shifted by 1, and we have an A star, and also again lot of copies of A1 and A star, etc. And we end with here a tensor product of copies of A1, and here we go to A. So we will send an element of the shifted multidual to some element of this home space, which is given. So if we apply it on arguments like this, as up to a sign coming from the causal rule, this thing. So here we apply our element of the multidual to the elements SA1 to SAK, and we produce, thanks to this, K elements, so a tensor product of K elements of A shifted by minus D. Then we, in some sense, shift all those elements to have elements of A, and the K minus 1 first elements of A will be, so we apply on them the maps Fi. So here, all the Fi are elements of A star, meaning that this is a map going from A to K. So here we have an element of K, and here we just only shift the last output of this map to have an element of A. So finally, here we end with an element of A. So this map is part of some proof one can make of the following statement. So namely, it is possible when we require an element in this to be cyclic with respect to the natural bilinear form to get an element of the same home, replacing the A here by an A star. And when we have so an element in this and an element of the same home with an A star here, we have an element finally of the space of Orchilcott chains of A plus A star. So this is an infinite structure, provided that here we have a pre-Calabi-Yau structure. So in fact, this map is also related. So if we have the necklace bracket, the map applying on the necklace bracket here of 2 elements will give us the Gerstenhaber bracket of the 2 elements where we have applied the map before. And this is why we have this following theorem. So if we have a finite dimensional graded vector space, then the data of a pre-Calabi-Yau structure on A, so an element in here, is equivalent to the data of a cyclic infinite structure on A plus A star.
Oh, sorry, I think we have put some conditions that A is subalgebra, infinity subalgebra of this direct sum.
Yeah, that's true. So this, in fact, yes, this pre-Calabi-Yau structure on a finite dimensional graded vector space should be equivalent to the data of a cyclic infinite structure on this space that restricts to A. Okay. So if this is true, sorry, if I add here the condition that A should be an infinity subalgebra of this space, or equivalently, so one can say that this infinite structure can as to restrict to A. Yeah, thank you. So yes, we have also this assumption, but this give us so an equivalence between the pre-Calabi-Yau structure on A and a cyclic infinite structure on A plus A star, that such that A is an infinity subalgebra of this one. So the finite dimensional assumption is useful to construct a pre-Calabi-Yau structure coming from an infinite structure, and also to say that this is cyclic instead of almost cyclic. But in fact, it's possible to construct a pre-Calabi-Yau structure, coming from a pre-Calabi-Yau structure, it's possible to construct a normal cyclic infinite structure on this space without this finite dimensional assumption. So I will now talk about the relation between infinity morphisms and pre-Calabi-Yau morphisms. And so I will first give you the notion, the definition of both those notions. So if we have infinity algebras A and B, an infinity morphism between them will be the data of maps like this of degree 0 that satisfy those identities. So here, this member is, so it seems like the Stashev identities, because one can depict it like this. So here we have a map F with, so going into B shifted by 1. This is why we have a bold arrow here that takes lots of identity maps, an output of a map MA, which is the infinite structure on A, and which take a lot of identity maps here. So we want the sum of all those diagrams of a given type, let's say n. So if the number of incoming arrows here is n, to be equal to the sum of all the diagrams of the same type. So we want also the sum of all the incoming arrows here, so all the size of the double arrow to be n. And here we have the infinite structure on B, which also have shifted outputs. And we have, for as inputs of B, lots of maps F, so of any size, such that the sum of all the size here are n at the end. So we want those two, in some sense, to be equal. And now I will record the notion of pre-Calabi-Yau morphism, which is a very recent notion, and which is a notion introduced by Kontsevich, Takeda, and Vlassopoulos. So a deep pre-Calabi-Yau morphism, F between deep pre-Calabi-Yau algebras, is the data of an element of the shifted invariant multidual now of A and B, which has to be an element of degree 0, and which will satisfy the identity. So again, we will sum over all the diagram of a given type, n1 to nk, and we want this to be equal to the sum of all the diagram of this form of, again, the same type, n1 to nk. So here we have now a deep pre-Calabi-Yau structure, meaning that we have lots of outputs. So we want those identities to be in the space of maps going from this tensor product to this one. So we will put in all, so we'll put some maps F in all the outputs of MA in order to go in B and no in A. And here, so we have elements in A in the outputs, and all the outputs are the outputs of F, so are in B. And also, so the sum of all those diagrams of this form and of type n1 to nk has to be equal of the sum of all the diagram of this form now and of type n1 to nk. And those diagrams also represent maps going from this tensor product to copies of, to a tensor product of copies of B shifted by minus D, because here we have the pre-Calabi-Yau structure in B. So we have a lot of outputs in B, And we take as inputs the outputs of maps F that are in B, or the maps F as have their input in A, and we have still some outputs of F because they are in B. So it has a sense to say that this one has to be equal to this one if the type is the same. So I will now state the main theorem that relates the infinity morphisms and the pre-Calabi-Yau morphisms. So if we have pre-Calabi-Yau algebras A and B and a deep pre-Calabi-Yau morphism between them, then there exists, so we can construct an infinite structure on A plus B star shifted by D minus 1, and also infinity morphisms from this infinity algebra, so this space with this infinite structure, to this infinity algebra and this infinity algebras. So those two infinity algebras have their structure given by the theorem by Kontsevich, Takeda, and Vlassopoulos, given the equivalence between deep pre-Calabi-Yau algebras and cyclic infinity algebras that restricts to A. But I don't assume here to have finite dimensional graded vector spaces, because as I said, I can, for this sense, so for this equivalence, for this sense, I can just come with a deep pre-Calabi-Yau algebra and then induce cyclic infinity, so almost cyclic infinity algebras without this finite dimensional assumption. So note that here the infinity morphism constructed are not strict anymore, and the infinite structure is not almost cyclic in general, but one can just add some assumption on the deep pre-Calabi-Yau morphism in order to have a normal cyclic infinity structure, which will be almost cyclic with respect to gamma of phi 1. So phi 1 is the first component of the deep pre-Calabi-Yau morphism that just go from A to B. And so it has a sense to talk about the phi 1 mixed bilinear form. So I will now sketch the proof of this theorem, and I will begin with some preliminaries for the proof. So I will define three graded vector spaces. The first one is, so B of AB is the product of graded vector spaces. So those are Hom spaces of a tensor product of copies of A1. So here we have K groups of copies of A1, of A shifted by 1 in some sense. Here we have K minus 1 outputs in B shifted by minus D. And we have the last one, which is A shifted by minus D plus B star shifted by minus 1. So I will also define BA of AB, which is so the same product here, and it's almost the same as before, but here we have as last output only A shifted by 1, which is in fact A shifted by minus D shifted by D plus 1. I finally define B of B, which is, so we have again the same product here. And we have here a group of inputs in A shifted by 1, an input in B shifted by minus D, and other groups of inputs in A shifted by 1. Here we have K minus 1, so a tensor product of K minus 1 copies of B shifted by minus D. And in fact, so we put all the inputs into groups, and we have, and so the number of outputs we have in all our graded vector space, so in all our graded Hom, the number of output is the same as the number of groups of inputs. Here we have K minus 1 outputs, and we will take this first, so this tensor product with 3 factors as only one group, and the other, so this will be a group, for example, and since this one is only one group, we have at the end k minus 1 groups, and this is why we have here k minus 1, a tensor product of k minus 1 copies of B shifted by minus D. So in fact, there's 3 graded vector spaces are related as follows. So we have an isomorphism between the shift by D plus 1 of B and the direct sum of BA and BB. So how is this isomorphism? We send an element of the shifted B to 2 different elements. So the first one is in BA, and it's given, so it's a map going from tensor product of copies of A shifted by 1 to the same. So here we have k groups of inputs. Here we will have a tensor product of k minus 1 copy of B shifted by minus D, and the last element will be in A shifted by 1. So here we just apply this map on elements, is the same as applying F on elements, which gives us so k minus 1 elements in B shifted by minus D that we will let as they are. And the last output of this F is an element of A shifted by minus D plus B star shifted by minus 1. So we shift this element and then take the projection of A shifted by 1 in order to get the last output as an element of A shifted by 1. So this is like the easier map. The second is as follows. So here F2 has to take in argument elements of A, an element of B shifted by minus D, and other elements in A. It will be up to a sign, the same as applying F on all the elements of A, which give us as before just k minus 1 element of B shifted by minus D that we will let like this. And it gives us also an element of A shifted by minus D plus B star shifted by minus 1. So we take the projection to the latter, and we thus have the last element here as a map from B shifted by 1 to K. So we apply this map to the element SB, and we end with an element in K here. So at the end, we really have K minus 1 element of B shifted by minus D as wanted. So I will now give you a map going from the shifted B to the space of Hochschild cochains of A plus B star shifted by minus 1. So I recall that an element in this space can be an infinite structure on A plus B star shifted by D minus 1, provided that it satisfies the Stashev identities. So this map is as follows. So we take a shifted element of B, and we will define an element of this as, so we apply it on argument. So here we have elements of A, an element of B star, an element of A, etc. And so this application is given up to a sign by this. So here we apply our map phi to all the elements of A. So this gives us K minus 1 elements in B shifted by minus D that we will use as argument for the maps in B star shifted by D minus 1. So here we end with an element of K, and we just let the last output, so with some shift of the phi here, because the last output here is an element of A shifted by minus D plus B star shifted by minus 1. So we shift it by D, and we let it as the output we want in A plus B star shifted by D minus 1. So this map is injective, and it's in some sense a generalization of the previous map. That was the map going from the multidual of A to let's say something that is included in the space of Orchil cochains of A plus A star shifted by D minus 1. So this map is kind of generalization, and one can use it to say that if we have an element in here, then we have so an infinite. So if this element here satisfies some condition, then we have an infinite structure on this. So in order to construct our infinite structure on A plus B star shifted by D minus 1, we will first construct an element in this graded vector space and then apply this linear map. So the construction of the infinite structure is as follows. So we want to define an element in here, and using the previous proposition that give the isomorphism between B of AB shifted by D plus 1 and the direct sum of BA and BB, we will define this element with those two components. So here we will have an element in BA, and we define it with some kind, so with this kind of diagram. So here we have the infinite, here we have the pre-Calabi-Yau structure on A. So we have outputs in A. We will let an output in A to be the last one, because the last output of this space is on A, and all the other output will be given as input of phi, where phi is the pre-Calabi-Yau morphism between A and B considered in the theorem. So here we have lots of elements of B shifted by minus D and an element of A1, giving this as a map, which is an element of BA. We do almost the same to have an element of BB using now the pre-Calabi-Yau structure on B. So here we have an input of B, which is in fact an incoming arrow in a diagram in B is the same as an outgoing arrow of the same diagram in B star. So this represents the output, the last output of this Hom space, which is in B star. And here we have lots of outgoing arrows that represent outputs in B. And here we take as input of the pre-Calabi-Yau structure MB, the maps, so some outputs of the map phi. Here we also have some outputs in B, so we let them. And thanks to those two diagrams, one can define two elements, and using the isomorphism before, those two elements give finally an element of B shifted by D plus 1. So the infinite structure on A plus B star shifted by D minus 1 is just given by J of this element we just construct, where J is the previous map going from B to this space of Orchil cochains of A plus B star. I will now explain quickly to finish the construction of the A infinity morphisms. So we want to construct A infinity morphism going from A plus B star to A plus A star in a side, and A and B plus B star on the other hand. So I will first define maps. So a map phi A star going from this space to A star shifted by D. And so if we apply here on those elements that are elements in here, and we apply to an element in A shifted by minus D, we will end up to a sign with an element, so we'll end with an element in K, the base field, which is up to a sign this map phi. So this is again the pre-Calabi-Yau morphism between A and B, which is a data for us, and we apply it to all these elements, considering now this as only one group. So here we have k minus 1 group. So this leads to k minus 1 elements of B shifted by minus D. And applying those maps, we finally have an element of K. I also define maps phi B that go from the same graded vector space as before, and that go to B shifted by 1. So I apply on element in here, and I will again use the pre-Calabi-Yau morphism to apply it on all the elements in A. This will produce K elements in B shifted by minus D. The K minus 1 first will be argument of F and will then give us an element in K. And the last one, so which is an element of B shifted by minus D, will be just shifted by D plus 1. So finally we have an element in B shifted by 1 as we wanted. So now in order to construct the A infinity morphism, so I will begin by explain the construction of phi A, which is an A infinity morphism going from this infinity algebra to this one. Its first component, so the component which really goes just from this direct sum to this one, will be the identity of A1, so from A1 to itself, and the dual, so the shifted dual of the first component of the D pre-Calabi-Yau morphism. So since the D pre-Calabi-Yau morphism go from A1 to B1, so phi 1 goes from A1, A shifted by 1 to B shifted by 1. So this really goes from B star shifted by D to A star shifted by D. So this is for the first component, and the other components that are not the first one, we will define like this. So if we compose this map in order to project on A star shifted by D, we have the map phi of A star that I defined before, and the projection of A shifted by 1 is 0, meaning that this A infinity morphism has only its first component that go into A shifted by 1, and all the other components leads just to elements in A star shifted by D. We do almost the same construction for the morphism phi B. So the first component is given by phi 1 going from A1 to B1, and the identity of B star shifted by D going from this space to itself. We define all its other components like this. So the projection on B shifted by 1 of this component is just the morphism phi B that I defined before, and that really goes into B shifted by 1 by definition. And all the other components, when we apply the projection on B star shifted by D, they vanish. So we only have the first component of this morphism that goes into B star shifted by D, and all the other components just go in here. So I now let you with some bibliography, and so thank you all for your attention.
Thank you very much. Can we all unmute ourselves and give the speaker a round of applause? Okay, if you have any questions for the speaker, you can ask them now.
Could you explain, Marion, these extra conditions that you mentioned to make the theorem that the structures were also almost cyclic and the morphisms were cyclic and so on?
Yes, so in fact, the morphism, so we have some particular case of this theorem. So let me just, yes. If we have strict de pre-Calabi-Yau morphism, meaning that all the component vanishes except the first one going from A1 to B1. Then the infinite structure constructed here is almost cyclic without any assumption, and the morphisms are cyclic, whatever that means. But we don't have cyclicity for the morphism in the general case. However, with some assumption on the de pre-Calabi-Yau morphism phi, the infinite structure will be almost cyclic, and this assumption is, so I don't have the picture here, but it's in some sense we want this diagram with the correct type and the sum of all those diagrams to be equal to this one, and we will add an assumption requiring that a particular case of this diagram has to be equal to a particular case of this diagram. So namely, the condition is as follows. If we have here diagrams of this form with an F1 here, so F1 is a disk, is represented by a disk with one input and one output. This is the first component that go from really A1, A shifted by 1 to B shifted by 1. So if we have a F here, which also take as its output the bold output, so the last output of the diagram, then we will ask that if the bold output is here, it's immediately flowed by F1 with only one input and one output. I don't know if it's understandable, but yeah, the condition is just requiring that a particular case of those diagram is equal to the particular case of this diagram.
Okay, thank you.
Yeah, thank you. Any other questions for the speaker?
So just want to clarify. So you have just a construction, not equivalence between something and something, yeah? Is it true? Is it true?
Yeah. In fact, so we don't have
kind of conversely from such, yeah, you cannot.
It's not an equivalence between because the infinite, both the infinite structure and the infinite morphism depends on the de pre-Calabi-Yau morphism. And so yes, we only have in some sense a functor from the category of de pre-Calabi-Yau morphism of de pre-Calabi-Yau algebra, sorry, and a particular category which whose objects are so infinite structure of this form and whose morphism are the data of an infinite structure and of morphisms like this. But I don't have the converse in order to have from an infinity morphism a pre-Calabi-Yau morphism.
But it is somehow at least compatible with composition of morphisms of pre-Calabi-Yau algebras, isn't it?
Yeah, that's true. In fact, if we take the infinity, so the category of infinite structure of this form and whose morphism are given by the data of both an infinite structure on this and two morphism like this. So in fact, this is just a partial category in the sense that we don't know in general how to compose some such morphisms. But if two morphisms here comes from two different pre-Calabi-Yau morphism, let's say pi and psi, then it's possible to have the composition of, so if we can compose pi and psi, then we will, then the morphism here are composable, and we can, so if phi go from A to B and psi from B to C, it's possible to add here the B plus C star and here the C plus C star, and to make a big hat in some sense to have the composition of those two. So this is really some kind of functor in the sense that composable pre-Calabi-Yau morphism are mapped to composable hats of this form.
Okay, thank you. Thank you.
Thank you. Any other questions or comments? Well, in that case, let's thank the speaker once again. Yeah, so the video of this talk will be uploaded to the YouTube channel of the seminar series. Yeah, thank you all for coming. Let's stop recording now.